Okay, great. Okay, so if I read this little situation here, so Mrs. Blanford, who taught this class AP Calculus AB many years ago, she's retired now, persuades Mr. Dooley to get a Twitter account. His handle is at second most happy place account, ends up with 30 followers after 3 hours and 100 after 5 hours. Just a little aside, you guys see how second happiest place and SHP kind of go together? Yeah, okay, yeah, there you go. I didn't know that. It took me a few years also. Right? Is that mind blowing, right? Yeah, because it's a dual meaning, right? Cigar prep. And so Rich Yoy is a great marketer. And that's his marketing employee. Like, hey, after Disneyland, this is the best place to be, right? So anyway, yeah, in case you know. Now you know. Okay, whatever. All right. Okay. Now you know. All right, so let's talk about this. So rates of change is a big part of derivatives and calculus. So we're going to really focus heavily on change. Change is really what you want to key in on. So, for example, for the first 3 hours, how many followers does he gain? Or what's the change in followers from 0 to 3 hours? 30, 100%, right. That's totally right. How about from 3 to 5 hours? How many followers increase? How much do we increase by? 70, right. But we care about as a rate, right? So, because what if he gains 70 followers over 10 hours? That's not that significant. But he did over 2 hours, that seems to be pretty significant. So which time interval will we see the most rapid growth or fastest growth? Yeah, 3 to 5, 100%, right. And that's what we're going to be analyzing. And that's where we're using calculus and derivatives to understand rates of change. Like, for example, COVID counts, right? COVID was kind of slow about 5 years ago at this time. Then after a couple of weeks, all of a sudden, everyone's getting COVID, right? So, and so we can analyze COVID infection rates in the same manner, right? Like infection rates. It's all about rates of change. So for the first 3 hours, how can I calculate his rate? Well, that's pretty easy. That's just a slope, right? That's just 30 minus 0 over 3 minus 0, or basically 30 over 3 or 10. But in the next 2 hours, what was the rate at that point? 55. Yeah. So we call it the average rate of change. So it'll be 10 followers per hour for the first 3 hours. It's a ratio, exactly. Or 35 followers per hour for the next 2 hours, from hours 3 to 5. So one way to think about it also that might help, and I really want to emphasize the word average. Average is kind of a big deal. You really want to key in on that. Because on average, how does the followers change per hour? Like in the first hour, did he gain 10 followers? No. What if he gained 25 followers in the first hour and then 5 followers from hours 1 to 3? Still, the average rate of change would still be 10, right? It's kind of like if you drive from here to Los Angeles. What if the distance is 400 miles and you drive for 5 hours? What's your average speed? 400 miles, 5 hours. 80, right? But you drive 8 miles per hour the whole way? No. Maybe you might for a good chunk, or maybe you might gun it and then you see the cops, you got to slow down, or you got to stop and get food or gas. I don't know. But, but the rates would change. And we'll look at that as tangent lines later on today. But for now, we're just focused on average rate of change. And really, it's just going to be a slope. Just so you know, the average rate of change, all it really ever is, don't make it seem like it's, I know it sounds kind of fancy. All it really is a slope. That's all it is. I'm going to be a little more specific and call it the slope of a secant line. In case you guys forgot from Geo Honors last or 2 years ago. So if I drew this, and if I drew this, what would that red line be called? Yeah, because it touches one point. Exactly. Well, correct. Well, the green one. Correct. That's a secant. Okay. A secant is when you pass through 2 points. So if I have 2 points here, and I draw the line connect those 2 points, that slope is that right there. It's the same thing. So the slope of a secant line is the average rate of change. So if I were to plot my distance right from here to Los Angeles versus time, where distance is y and time is x. And if I were to draw a line connecting my starting point 0, 0 and my ending point at 5, 400, that slope would be my average speed, right? Of course, the speed could change at various times in that interval, but still we're looking at the average rate change. So that makes sense, right? And same thing for 3 to 5. If I drew a line between these two, and it's kind of hard to draw that line, that slope would be 35. Okay, questions so far? No? All right. So, other things you need to know about, rates of change don't have to involve time. Usually when we think of rates of change, think of time, like how much water is being flowed into a cup, or I don't know, speed, things that were, or how many people are getting sick per day. We could look at it like that, but it doesn't have to involve time. Like, look this case here. Let's say Mr. Dioli gets 4,000 retweets for his first 4 tweets, right? So let's say after 4 tweets, he gets 4,000. But let's say the curve does something kind of funky. Like that, right? If all I'm interested is average rate of change, I'm simply just going to do 4,000 over 4. Or 1,000 retweets per tweet. So if I draw a red line here, or a pink line, that slope would be 4,000. Sorry, 1,000. So it doesn't have to involve time, just so you know. All it ever is a change in y over change in x. And the context matters. You know, whether you're dealing with like time or tweets or whatever, or followers or distance, time. I mean, you know, just depends on the context. So that's all there is. So let's look at number 1. How would I calculate that average rate of change for that function? Well, ln x looks like this. This is why we spent all this time having you guys learn these graphs, because by now you gotta be able to do these graphs pretty easily. You gotta be able to say, okay, here's a graph. Let me find the rate of change between 4 and 12. You gotta be very comfortable with these graphs in the domains. So that's how the ln x looks. How do I calculate it? Do this. I'm going to punch this in the calculator because I cannot do that in my head. 1.0986 over 8. We'll go 3 decimal places. That's kind of standard on the AP exam. By the way, if this were an AP question, it wouldn't be too easy, by the way. But if something like they ask, like maybe they might do a table, perhaps they might give you a table of values. Say, oh, find the average rate of change. They might. I've seen that before on recent tests. You can even answer like this. Actually, let's look at that.
You have to write ln 12 minus ln.
Yeah, right. You have to write ln 12 minus ln 4. Yeah, you do have to at least show that you're evaluating. If you wrote ln 12 minus ln 4 over 12 minus 4, you don't have to simplify. You can leave it unsimplified. They would still be the full code. Just so you know. And I know when you guys start taking AP Calculus next fall, you'll be reminded of that. But yeah, 0.137 would be my answer. And if I were to plot, I'm going to go to Desmos in a moment. Because I'm going to show how I can graph that, just to verify that I've done this right. So yeah, if I go to Desmos, let's find Desmos here. Let's see here. Y equals ln x. Here. And by the way, you could actually punch in points if you want to label them like that. You could totally do that. Okay, see how the points right there? Now, how would I draw, or how do I write the equation of that? You guys see what I'm doing here? What form is that called? Point slope, yeah. Point slope is very popular. See, it goes right through it. So that makes sense that the slope will be 0.137. Yep. Totally makes sense because it passed through those 2 points. Okay. So questions on example 1.
Sorry, that's it. You're just kind of lost.
Sure, go, yeah, please, ask, yes, go ahead. What about natural log?
Just example.
Just an example. There's no deep meaning behind it. We're just showing you, we're just applying the average rate change to an equation.
Okay.
That's all it is. Yeah, that's all it is. So let's do it to another equation. How about x cubed? So that should be pretty straightforward, right? So now I know what's going on. I'm going to do 2 cubed minus negative 2 cubed over 2 minus negative 2. Easy peasy, right? Should get 16 over 4. You should get 4. And x cubed looks like this. Let's go green. If I draw a line to those 2 points, yeah, actually they're pretty good, pretty well there. That's slope of 4. So yeah. So what does this remind you of? Slope. That's all it is. Change y over change in x. That's all we're talking about. Here's yet another example. And by the way, it's okay if it crosses the line, the curve at other places. All I care about starting and ending, start to finish. That's all I care about. So that's average rate of change. Questions? Pretty straightforward. All right, now we get to the fun stuff.
Pretty fun.
Yeah, well, thanks. Well, it's like happiest place on earth. That was kind of fun. All right. Y equals x squared. Let's focus on that. And 1, 1. We're gonna find the slope between point P and various values of point Q. And we're gonna notice that as point Q gets closer and closer to point P, the slope is gonna eventually converge to a certain number. Before we do that, just a quick rundown of I already did this with you guys, but that's a tangent line. We know this, right? That's a secant line. So what we're doing right now is we're doing the secant line for between point P and all these iterations of point Q. Ultimately, it's going to become a tangent line once Q reaches P. Once Q becomes P and they coincide, it becomes a tangent line. So that's gonna be our goal. Our goal is to have P or Q, let me take it back, Q approach P. Or delta X approach 0. That's my goal. And we're going to try to evaluate the slope as a result. Okay, so let's do this right now. So let me show you can do this kind of efficiently in the calculator, because I know it gets to be kind of a pain to do these over and over again. So let's see here. Math departments. That fit really nicely. Here we go. So I'm going to type in x squared. And if you guys remember, alpha trace is where you can locate y1. So I'm going to type this up, just kind of get queued up here. Actually, let me delete that parentheses. And then what's my change in x, guys? The first one. 7 minus 1. Yeah, 6, yeah. So I get 8. Okay. Remember, all we're doing is we're doing that's what I'm doing, right? Okay, if you want to do it again, you can repeat, if you hit second enter, or if you just hit the up key and grab it, you can change that to a 5. But then, of course, you have to change your denominator. What's my denominator going to be now? How far is 5 from 1? 4. Yep. You get 6. All right. Let's rinse and repeat. Change that to a 2. Change that to a 3. 4. By the way, that'll be 2.25 and 1.69. For just y squared. Okay, let's do it again. Because I can do math in my head really well. Sorry, I was a little arrogant. No, it's just I from the last class.
Yeah.
Well, I know 1.5 squared. I yes, I can do it in my head. And plus, I've done these notes for 15 years, so I know these notes nice, like back of my hand. Pretty much, they work. We do tweak. We haven't tweaked these in a while. That's 2.5. Let's do it again. Ah, geez. Here we go. Two point three. Two point one. So what is it converging to?
2.
Yeah, it's getting closer and closer to 2. We'll prove it in just a little bit. If you hit insert, you can insert a 0 there. That'll be 0.01. Yeah, 2.01, right. So we're noticing that as x approaches 1, or delta x, what's the slope approach? 2. So it's a limiting case. Hence why we spent all this time on limits before this. And if I look at the graph one more time, here's 1, 1. Ultimately, what's going to happen when these 2 points coincide? What do I wind up getting? The tangent line. And that's where we're working our way towards. So this is working our way towards a tangent line. Ultimately, when Q coincides with P, that will be a tangent line, and we're trying to find that slope. So we treat it like a limiting case. So as you see here, yes, there appears to be a limiting value. It appears to be 2. And the limiting value, because this is called the slope of the curve at point P, or the tangent of the curve at point P, or it's called the derivative, which we'll talk about on Thursday. We'll use that term more often. The derivative of y equals x squared at x equals 1. And the derivative is a rate of change. It's actually an instantaneous rate of change. Because at the instant x equals 1, and we're going to emphasize that word big time on Thursday. Instantaneous rate of change. It's instant that the curve changes by that amount. So y changes with x at a ratio of 2 to 1 when x equals 1 at that moment. So if you're like driving from here to LA, after the first hour, what's your speed at that moment? That would be a derivative or a tangent line. If you took your distance curve and do a tangent line at x equals 1, that would be your speed at that moment. And we'll talk about speed as speed as an application of the derivative, or linear motion. We'll talk about that probably next week sometime. I think physics, yeah, 100% physics. Physics is a big deal here. Not quite physics C, but
We're doing derivatives.
well, integrals would be part of physics C as well. All right, excuse me. Let's keep moving. Okay, so here's what's happening. Let point Q be the following. Okay. So we'll let H is like delta X. Think of h as like the difference between point P and Q for x. Okay. So h is like delta x or b minus a. And get used to that word delta. We're gonna use the word delta a lot in this class. So delta x is a change of something. So in this case, the change in x. So that distance is h, just so you know. Now point Q, it could be to the left or right. It's up to you. So h could be positive or negative. Doesn't have to be positive. Usually we keep it positive, keep it simple. But to find the slope, that's gonna be your change in y. You guys know this, right? Over change in x. So what are your y coordinates here among P and Q, or between P and Q? What's the y coordinate of the first point? 1. And this will be 1 plus h minus 1. Okay, let's work it out. That's gonna be 1 plus 2h plus h squared. And down below, just get h. Ones cancel. Factor on h. What happens to the h's? Let's get 2 plus h. However, it has to be a limit as q approaches p. So as h approaches 0, what was my slope approach? 2. So that's how you want to think of like that. So you do this algebra to kind of simplify it in some ways, and then plug in 0 for h afterwards. I can't plug in 0 right away, because if I do, that's gonna be a problem, right? But oh, okay. All right, so let's keep moving. I understand what okay, but it's good. It's good. You find something cool. Good. Love it. So the equation tangent would be this. Right, pretty simple, right? So that's the slope. Or we could call it the derivative as well. And of course, you have 1, 1. And by the way, point slope form is a preferred form. Do not bother putting in slope intercept form. You can if you want. It's extra work. And if you do it wrong, you actually lose points. So best not to do it. So just leave it in point slope form. So again, that's the preferred form, point slope form. So if you look over here, the slope of the curve or derivative, same thing, is defined as this. The limit as h approaches 0 of fa plus h minus fa all over h. Remember, h is just delta x. It's just that. The bottom becomes that. More specifically, we actually call this the limit definition of the derivative. So let me erase that. Instead of calling it the derivative, I'm going to call this the limit definition of derivative, because there are other definitions we'll see later on. But at its core, it's going to be the slope of the tangent line. So you're looking at a rate of change here. We could also call it tangent to the curve. That's fine. So like, for example, that would be a tangent line, right? Now, what does the word normal mean in terms of physics? I know for some of you guys taking physics, some juniors here. Perpendicular, yeah, yep. It'd be a perpendicular line. So like, you don't have to draw this, but like for those who are taking physics, you guys have probably dealt with ramps, right? And you have like a box and a ramp and it slides down, you'll get friction, all those things. That's called the normal force, because it's a force that's perpendicular to the surface that it's sliding on. So normal just means perpendicular. So what would be the slope of the normal line to this one? If I have 2 as my slope, what's my normal slope? -1/2, exactly. Negative reciprocals, right? Okay. Cool. All right. All right, now the real fun begins. Okay. So we're gonna find the slope of the curve at x equals 2, or the derivative essentially. So it's a funky curve. I don't know sure how it looks exactly. I think it kind of looks like this. Think it looks like that. 100% sure.
What do I say this? No, I go like this.
I think. I could be wrong, but let's do it. Here we go. You can say the limit.
That's.
Thanks. Yeah, I thought it was pretty good too there. Okay. That's your setup. You have to set it up first. So I'm using the formula on the previous page. Then you have to do some algebra. Now, I take it that Mr. Van probably didn't teach you guys binomial expansion.
Probably.
Okay. I'll have to teach that to you guys later. Maybe in sequence series we'll do. For now, just know if you FOIL that, you get that, right? Yeah. No, but we're gonna change that next year because he was in the CPM program and it wasn't in CPM, so that's not his fault.
Is there like difference of like difference of
Not quite. It's just an expansion of
oh
terms. If I plug in 2 plus h, it's gonna look like this: 2 plus h cubed minus 2 times 2 plus h. See if I can tuck all this in. Minus, we'll go green here. Because what does f of 2 equal, guys? Yep, equals 4. Yep, f2 equals 4. Okay, so you guys see what I just did? I replaced f of 2 plus h, but I also have to subtract with 4 because it's a slope, right? I'm trying to find the slope between 2 and 2 plus h. Okay, so now I get this. I'm going to do this. That's why I said this is where the fun begins. That'll be 8 plus 12h plus 6h squared minus, no, plus h cubed minus 4 minus 2h minus 4. Actually, I'll do green for that last minus 4. All over h. Okay, do you guys see what I did? I expanded 2 plus h cubed using that formula up above. 8, my a was 2, so I did a cubed. My 3a squared b is 2, sorry, 3 times 2 squared times h. 3ab squared is 3 times 2 times h squared. So h cubed. Okay, we're good. Things should cancel out very nicely. You should expect all the whole numbers to cancel, by the way. You should only get h up top. Because right now I can't plug in 0 for h. I want h to cancel eventually. But if you don't get h to cancel, you're doing something wrong, just so you know. You're clearly doing something wrong. Or I just gave you a problem that doesn't really work. It's your fault, my fault. All right. That should be 10h, by the way, right? Yeah. And by please don't get lazy. Please write your limit notation. You guys did a much better job compared to the other classes. I had a handful of the other classes that were really lazy with their limit notation.
G period.
Yeah, that G period. What happens to H here? Okay, now I could actually, and actually I'll just be a little more detail oriented. I know I'm kind of being a little OCD. I'm kind of showing all the steps here. If I plug in 0, I should get 10. Just 10. Yeah, that's it. Just 10. No, not really. But one thing I saw some people do this. So some people doing this and they leave their answer like that. You're not wrong, actually, because that is true. Because what's the limit of h approaching 0 of a constant? It's just still a constant. So you're not wrong. It's just kind of bad form. So just write 10. You don't have to write the limit. Once you've evaluated, you don't have to write the limit of t. So sometimes you guys write the limit too many times. So just be mindful about that. Now the tangent line. I'll squeeze it over here. For part B, how to write the tangent line? Y minus 4 equals 10x minus 2. Does that make sense? You guys agree with that?
Where did you get 1 minus 4?
Where do you think I got from? What does that for 2 equal? Yeah, point slope form. Correct. Point slope form. And C would be y minus 4 equals negative 1/10. X minus 2. Okay, so all's good.
Wait, why'd you use H?
What was that?
Why'd you use H?
Well, that's part of the formula because H represents the change between the change in X between the 2 points. So, because what I'm trying to do is I'm trying to find the slope of the secant line between A and A plus H. If you go back in the previous page here, so this is kind of the theory behind it. And it's a great question you're asking. So, oh, geez. So see how that's A, and that's A plus H, right? So they're not together right now. They're far apart. What's the change in X here? A plus H minus A, or H, right? And what is our goal? As we mentioned earlier on, our goal is to get H to be 0, or delta X to be 0. That's why we use. Can I use a different letter? Sure, I can use delta X. I didn't have, but that's just the kind of standard that's used. So, but H represents a change in X between the 2 points. We want that change to be 0, because ultimately the secant line then becomes what? A tangent line. And if it's a tangent line, that's now called instantaneous rate of change. The rate of change at that moment. And that's what a derivative is. And that's the whole essence of this unit in the pretty much first semester of calculus. Yep.
So it says find the slope of the curve at x equals 2. How
Yeah.
can you find the slope of the curve at 1?
Oh, what? Sorry.
Like 1. At 1.
Well, no, that's what I did. So I found it's a limiting case. So here's the curve looks like this, right?
Yeah.
So this is like 2 and 4. I know this is not to scale. So I'm trying to find that slope, right?
But where's the other point that you?
How's that not different from?
So the other point could be like right here, let's say, right?
It has to not touch any of them.
What do you mean the other point? There's
So there's
one. There's only 1 point.
Hold on.
You get what I'm saying? How can you find the slope of the line?
Give me a sec here.
because it can't touch the line again.
But it can't, it has to touch at least one at a time.
Okay,
So-
okay, first off, do you see what's happening? I have 2 points on the curve, right? And if I just like simply do f of 2 plus h minus f of 2 over h, right? I wound up getting like a bunch of stuff, right? Like a bunch of stuff with h's, right? And I divide by h. I think, what was it? It was like 10 plus, what was it again? 10 plus 6h
6h cubed.
or h squared.
H cubed.
It's six,
Wait, it-
H.
6h plus h squared.
Yeah, thanks. Okay. That's what I got afterwards, right? Okay. But so if h was not 0, right? If h was like say 5.6, let's say, right? Then I could use this expression to find the slope. Right? I just plug in 5.6 and I get my answer, right? Or let's say h is like 0.1. Okay, I'll plug in 0.1. It'd be like 10 plus 0.6 plus 0.01, right? It'd be 10.61, right? Let's make h even smaller, like 0.00001. What happens as h gets closer and closer to 0? 0.00001. What happens to these 2 points here? They eventually get closer and closer together, right?
Points what closer to it.
Right. As h gets closer to 0. When these points get closer together?
Yeah.
Okay, so it's still a secant line, but it's looking awfully like a tangent line. It's looking awfully close. Is it exactly? No. Is it approaching it? Yes. And it's all about approach.
So, but when h equals 0, then.
But when h does equal 0, so once we do the algebra and simplify everything as neatly as I just did right here,
So this is the slope of the tangent.
correct. Right. That's what it is.
The slope of the curve is x equals 2.
It's the slope of the tangent line.
I thought it was the
No. So sorry, I probably was a little too long-winded with my response. You were just asking. Okay, now it's a semantic thing. Sorry. Well, anyway, hopefully you understand the theory. But the slope of the curve is a tangent line, just so you know. It's the same thing. All right, here's what I want you guys to do. We still got plenty of time. Try example 5 on your own. This will be a fun one because it involves find the least common denominator. Also try example 6. I'll show you guys the answers in just a moment. Or actually, it'll take a few moments. But when you start example 5, start by doing this. So you do 1 over that's what you're gonna do. Okay.
Right. Right.
Yes, sir.
So, sorry, why do we start with it over H, not H?
Because what's the change in X? Because your inputs are 5 and 5 plus H.
Oh, yeah.
Yeah.
It says 5 plus H minus 5.
Right, right. You guys got an answer for 5? Yep, good. Yeah, and again, this is why we spent all this time in Algebra 2 in this class to understand all these graphs and how they behave. You guys should know that this is a graph with a vertical asymptote or infinite discontinuity at where? At 3. And a horizontal end behavior asymptote at 0, right? And the branches look like this. And if you look at x equals 5, which is probably somewhere over here, what's the slope of that line? It's a negative slope, clearly, right? And also the function is decreasing, which means the slopes will always be negative, regardless of wherever you are. always gonna have a negative slope, which is a derivative. And we're gonna talk a lot about that over the next few weeks. So you're really kind of just getting that deeper understanding of what's happening to these graphs, these functions. So that's the beauty about calculus. It gives you that deeper understanding. Go and try example 6 and we'll be all done. So example 6, you're gonna want to do this. You're gonna want to do this in terms of x. So you're gonna say 4 equals the limit. You're actually gonna do f of x plus h, which is kind of what we'll do a lot of in the next class meeting on Thursday. So you got this in terms of x. Yeah, this is a fun one also. Question? You're good, David? All right. I'll freeze the screen, let you guys kind of take care of the rest there.
What happened? What is before? What is it? Why is it 4?
Oh, because part A, they say the slope equals 4. Because they told me.
Oh, so you're like,
I'm trying to find an expression for the slope of the curve or the derivative. I'm trying to find an expression instead of equal to 4. I'm trying to solve for x now. So now I know my output, what's my input?
you have to multiply h to the other side.
Not necessarily, no. We clean up the right side. No. Yeah, they cancel out. Everything should cancel out very nice if you do it correctly. That's why these are fun. Told you these are fun because you look for a very elegant solution. Okay, that's kind of crazy, right? That's oh my gosh, 9 terms. But but you're gonna have like 3 pairs cancel. X squares cancel. 3x cancels. 1 cancels. What are you stuck with? Can I factor something out of this? You bet. Factor it out. H is cancel. If you plug in 0 for h, you should get 2x minus 3. That's going to be your derivative or your expression for the slope of the curve. So if the slope is 4, x will equal 7 halves. Or for part B, if your slope is 0, x will be 3 halves. So what this means, actually, before I do that, all this craziness with all the letters and H and cross and stuff out. Questions on the purple and green, the process here?
Oh, you put it 0.
No questions here? We're good? Yeah, H, factor on H, cross stuff out. The expression for the derivative will be 2x minus 3, or the slope of the curve. Instead equal to 4 to see, well, where on this parabola, where in this parabola the slope can be 4? Probably somewhere to the right of the vertex, right? So it's 3.5, 7 halves. Now, this is interesting. Look at part B. When the slope is 0, what's the significant point would that be? Or critical point called sometimes. What does that represent on the curve of the parabola?
The minimum.
The minimum, the vertex, yes. Because you've read the vertex, look at you, Sebastian. Go ahead. Good. Now, think of the vertex. Is that a high low point? What's the slope at high low points? That is a huge concept. Unfortunately, I don't think we'll get to that type of application. I'll try if we can. It's really hard calculus, but it helps you find extreme values, highs and lows. That's why it's so when you look at like the peak of the curve, like if you're projectile motion, how high something goes, that's calculus. That's using calculus. So yeah, anyway.
We do it.
I know. That's just a simple way, but there's other more complex problem. So, and we're all done.
Why do you think I get work?
I don't know.
It's just like.
All right, we'll stop.